Now this video is mostly a review for the 2020 team, but let's also take a moment to appreciate what we've learned this year in the software team. So we're going to talk about documentation, the command subsystem pattern, some technical problems we solved, and some solutions. And we'll talk about the difference between those. Should be no surprise, we've got to read the documents. Not only the official ones, but also the documents where Bradley's currently coaching, and we've got other resources that we found a lot. They're great stuff. We have to, every year, get a little bit more sophisticated by getting a little bit more serious about reading documentation. Okay, so next up is the command subsystem pattern, and this is about design patterns. Design patterns are really useful and a broader topic than right now, but this is really handy. So it's all about the way we organize our code and how we split functionality into different little reusable bits. So let's follow the thread, meaning let's see how the robot line by line computes and gets started using this pattern. All Java apps start from public static void main. Our robot's no exception. And what it's doing here is kicking off the robot.java file. And what's the first thing that robot.java does? It sets up subsystems. We've got 4 subsystems: our drive, the kickstand that tilts us back, our arm, and the elevator. So the lift up and down system for the arm. If we take a peek at the drive subsystem, for example, we'll see that the motors and the gyroscope and the other tools needed for our drive system are set up in this file. Rather than throwing everything in robot.java like we did before, we put it here. This provides the advantage not only of having more organized code, so we know the drive motors and the drive related material are all configured here, but we also can tell some other benefits that I'll get into in just a second. But to understand them, we need to look at commands and how a command is structured, and how it plays with this subsystem like a drive. And the way we'll start is looking at the first type of command, our default command. And this is one that is ongoing. It doesn't just execute something and then stop. It'll just keep on letting you drive the robot. So let's take a look at the drive command. I did want to highlight the set default command. So that means that when the drive subsystem has no other commands being operated, it'll fall back to this drive command. So when it's idle, it'll swing back to drive command. That's its default. Commands are all structured really similarly. They run a constructor, so you can set up some variables at the beginning, counters and useful factors. And then the init runs when the command is started. And this can be run a lot. If you have a button, so every time I press a button, it starts moving the arm. Each time you press that button, init is run. And then it will keep on running the execute and constantly check, am I done, am I done, am I done? As soon as is finished returns true, then the end is triggered and whatever shutdown operations you have are run. And once the end happens, then it'll go back to the default command. So that's the basic idea of a command. But we're not going to have one that ever ends with this drive command. So you can see the is finished here is always false. It will never run is finished. It'll always run is finished, and it'll always say false. What will never run is the end. Once is finished, it returns true, then end is auto run. What will happen instead is we will continually be interrupted. If I ever switch to a different drive command, like a button to turn it around 180 degrees, that'll take over and will run the interrupted. Until then, it'll keep on running a somewhat complicated execute code where essentially the important thing is right here. I take the value from the left Y, which is up and down, controller, and I'll take the value from the left stick on my Xbox controller the X-axis, the side to side, and I will drive the robot according to the proportions of that stick. So because it starts at 0, and as you move the stick forward, that actually goes into a negative. So we're switching this to positive. This is just because the robot turns opposite. So we made that negative as well. So that's essentially it. This has some additional drive straight, which is not being talked about in this video. This has some additional stuff where if you're not trying to turn left or right, we'll use the gyroscope to see what your original heading was, and it'll automatically make some course corrections to keep you driving straight if you weren't trying to turn at all. But the point of this command and this demonstration is that this command isn't ever finished. You have to interrupt it because it's just sitting here listening for the controller stick and responding the drive accordingly. Okay, so let's take a look at our kickstand solution. So this thing here, and we'll look at the requires function. This is the whole of the kickstand subsystem. It has one motor to power the actuator and one potentiometer. It's just an analog sensor to tell how far the kickstand has been deployed. It's not even wired up at the moment. And it's got no default method. It's got nothing in the constructor. Nothing needs to happen when this thing gets going. It just sits idle. But if we go back to our robot.java, you'll see that as it's setting up the elevator, the arm, the kickstand, the drive, it then sets up the operator input file. And the operator input file, this guy, sets up a bunch of buttons. So these are all the declarations. So it's just in Java saying, hey, I'm going to use something called a B button. It has a lot of properties of a button pre-programmed in Java and in the FRC library from WPI. Helpful stuff. Look for this Xbox controller plugged into your USB. It's button number 2. Now I have a variable. And so what I can do is if I press the B button, then do something. Or if I press the left bumper, then do something. And now it'll just have this command bound to this bumper. There's a couple ways to bind it. We can do when pressed and it'll just execute that command. Or it'll only execute the command while the button is being held and run the interrupt as soon as you let go. So that's what we have for the bumper. So you have to hold down the bumper to deploy the kickstand. And the first thing on this command file is requires. And the requires will grab this subsystem from the robot, and if anything else required that system, it'll automatically run the interrupt command on the interrupt function on that other command. And this is super simple. It's just while it's executing, the half power is deployed to the motor. Easy peasy. So we've got all sorts of commands that play really nicely with each other. So there are the endless commands, so like drive command that has no end. There are commands that we use in a really simplistic way, like the the kickstand down command we just looked at. But there are command groups now too, like drive adjust. So now this drive adjust runs sequential commands. So it'll turn to a 30-degree angle, it'll back up for 1.5 seconds, and then it'll turn back the other direction at 30 by 30 degrees, moving it back to its original heading. So this allows us to sort of make an S turn and back out of a situation and realign. This is one of the reasons why we have lots of simple little commands, and why we avoid having complex solutions all built into one command. We could have manually did these 3 steps in this one file, but by having them as separate modular components for each part of this command, we can then reuse them. Now this drive to angle helps us with the other one as well. And the drive to angle could help all sorts. A drive time reverse to back up for a certain amount of time is also something that we use for the disk release. So disk release is somewhere here. Yeah. And so we'll back up. So we'll lower the elevator for a certain amount of time and then back up. So all of these small modular elements are helpful. And so it might seem frustrating that we're making these many frequent little files and little commands, but they add up to be pretty helpful building blocks. All right, so we should study that more, but for now, we'll call it done. Now let's look at some of the solves. Solves, what I mean by that term is just a feature request, something that was requested of us, and trying to figure out some sort of technical, practical solution to make it happen. So really, our first one is not really PID. What PID really is a way. Normally, when we're trying to turn from here to here, our robot, it'll overshoot and then overcompensate, and it'll kind of, wobble back and forth. And you see that here, that we wobble back and forth. And there are mathematical studies on how to improve this performance. So how you can get to this red line where it's nice and smooth and gently lands exactly where you want it to. No wobble, no jarring motion that causes us to lose our panel. Just smooth execution. We don't know how to properly do this. We ended up hacking together a not really PID solution that really just uses the proportional piece of PID and not the integral or differential piece. But we basically just calculate how far we have to go and give it a proportional power to how far left we have to go, and then we do a couple hacky things to figure out which direction we're trying to move. Check it out when you can. Ask some questions about how this is wired up. This is something that Sebastian Williams actually put together initially. We've cleaned it up a little bit this year and made some improvements to it. But it's essentially the same idea. This next idea we stumbled onto while having a lot of frustrating problems with getting something to work for a specific time. Thread.sleep is usually how we do this in other classes. We just put the thread, it sort of goes brain dead for a while, and that can cause the robot to panic. And so we can't use thread.sleep like we used to. And so one of the eventual solutions we came up was kind of funny. So we know that this execute function is called repeatedly as our command is being executed. And so it's about 30 times per second. And so each time when our command is initialized, we set the count to 0. And this is an instance variable, so that means it's declared up here, but all the methods can see it. And it's not scoped to just one method, but because it's declared up here, all of them share. And so every time execute is run, count goes up by 1. That's what the plus does. And so once count is greater than or equal to 30 times however long you wanted me to do. So 1 second, that'd be 30 times. So once it's greater than or equal to that, it shuts off. It's not perfect because it's not exactly 30 times per second. And so the exactness is a little wanting, but it's so reliable and it's so simple. So we just run up a count on our execution cycle and then we shut it down. So while that's happening, we're driving backwards. And then once we run out of time, then end is automatically called and it shuts off the power. Okay, that's that. And the last one real quick. Instead of if statements, there's also switches, which takes a value from the D-pad of our Xbox controller and then responds to different conditions. And so in the usual case, if no one's pressing it, it'll get a -1 and it'll just break out of this. Otherwise, if I press down on the D-pad, it will execute a tidy 180-degree angle change, and then once that's terminated, it'll go back to the default drive command, and then just keep on sitting here in the execute loop, waiting to respond to another one of my D-pad things. So anyway, this is our switch. Pretty cool. Lastly is our solutions. Driving straight and some of these angle changes, it represents us as a software team trying to talk to our driver and see how can we make things better. Can we smooth out the turn a little bit? Can we try to keep you driving straight? Can we, how can we actually make things better? And that's what we're here to do.